Happy Friday. It's early afternoon for us. It's extremely early morning for Kayla. She's joining us from Hawaii for a Compass seminar. So Kayla will be presenting an hour seminar today. Kayla received an undergraduate degree in 2017 from the Environmental Resource Engineering State University of New York College of Environmental Science and Forestry. Her current advisor at UM is Ben Kirkman, and her research interests are atmospheric blocking. And today, her title of her seminar is Space Tidal Blocking Sensitivity to the North Atlantic Oscillation. And with that, we can view the abstract, and then I'll turn it over to Kayla.
We usually don't do this abstract reading for the 1 hour seminars.
Never mind, I'm sorry. All right, so Kayla, whenever you're ready, the floor is yours.
Okay, I'm just gonna share my screen. All right, are we good? All right, everyone, thank you for coming to my 1 hour seminar titled Space-Time Blocking Sensitivity to the North Atlantic Oscillation. So with that, let's get started and jump right in. Okay, I just have a small outline of the three sort of parts that I'm going to be talking about today. So we have blocking and overview, blocking with the NAO, and blocking in the ocean. So to start with part one, we're going to do the typical background and motivation type things. We're also going to talk about the methods and talk about the results of this blocking overview section. So first, let's begin with what exactly atmospheric blocking is. Well, essentially, it's just a reversal of the meridional gradient in the mid to high latitudes, typically representative of the geopotential height or PV gradient. It's also quasi-stationary, and it obstructs the zonal flow, leading to a split or diverted jet stream. It's also persistent and is a subseasonal phenomenon lasting a minimum of 5 days. So these characteristics, anomalous, large scale, and persistent, are what help differentiate blocking from other weather and synoptic phenomena. Further, the large scale and persistent are spatial and temporal constraints that are important moving forward when we start to classify blocking. I provided this image here from Wolling's 2018 to really show you what different kind of blocks look like in the atmosphere. I've also chosen this image because it's a little different of a spin, pun intended, on the typical geopotential height composite that you'll normally see with blocking. So what we have here is theta, or potential temperature, on a 2 PVU surface, right? So we're looking at blocking from a more of a PV perspective. And we're a lot higher up in the atmosphere, right? So 2 PVU. And here you can see our omega block, as well as our Rex or dipole block. Also featured is anticyclonic and cyclonic wave breaking, which also help generate this meridional reversal, something we're also going to be talking quite a bit about today. So why do we study blocking? Aside from they're really cool, which we've seen on the previous slides. Well, blocking has a lot of impacts on European and US weather, especially the Atlantic blocking events. This can be seen here in some previous work that I did, where I took the correlation of blocking intensity of Greenland blocking with temperature and precipitation anomalies. Just a quick look at this plot, you can see there is a pretty high correlation between temperature and precipitation anomalies. Further, we don't really have a comprehensive dynamical theory of blocking in the literature. It's not that we don't have one, it's just that we have many, and not one that fully captures the blocking life cycle from start to finish. This is also reflected in our ability to predict blocking, which we're pretty bad at. There's a strong negative bias in blocking frequency across both weather prediction and climate models. And while we're doing slightly better with later generations, it's a pretty small magnitude of an increase of doing better, right? And particularly this problem area is in the North Atlantic. So everything from impacts to theory to predictability. We have quite a bit of motivation to really study blocking, especially from new or multiple perspectives. So with that, now that we have a pretty good background on blocking, let's get into some of these methods, which I'm really excited to talk about. And so first is our blocking detection methods. And when I'm referring to detection, I'm really meaning blocking indices. And there are two featured in my work. The first one on the left is the PV theta index, or what I'll refer to as the PV theta index, because those who developed it deemed it that name. But really what we're looking at is the reversal of potential temperature on that 2 PVU surface. And that's why I showed you that composite of the blocks earlier, to really show you that PV perspective of blocking. Essentially what this index does is measures that meridional reversal, and without spatial and temporal constraint, which is needed to really detect blocking, if you recall, it is a Rossby wave breaking index. And so Rossby wave breaking is conducive for to develop blocking, as it creates these cutoff highs and you get that meridional reversal. And as long as the background flow is able to support the stationarity and the persistence, you get a block that develops, right? And so again, we have these spatial and temporal constraint to differentiate it from other weather or synoptic activity. Okay, so this is our PV theta index. On the second index that I use is the absolute geopotential, or Z500 millibar index. I will be referring to this index as the AGP index throughout. And essentially this is doing almost the same exact thing as this index, but measuring the reversal, the meridional reversal of geopotential height at each latitude and longitude. One of the differences between these two indices is that this index here has a threshold that needs to be met for the blocking count to start, right? So we need a persistence of 4 days, but this threshold needs to be met for those 4 days across our spatial constraint. This only has a spatial and temporal constraint, not a threshold, which could lead to some differences in my work that I will discuss later. So again, our PV theta and our AGP index. Further, Masato et al., whose PV theta index, curated version of the index I have applied, also developed a complementary classification index to the wave breaking blocking, or PV theta index. And so with that, based on the index value that you receive, you're able to calculate the direction of breaking occurring at blocking onset, right? And so when you get a positive direction of breaking value, you get an anticyclonic Rossby wave breaking, whereas negative, you get cyclonic, right? And so it's essentially determined on this phase space here. And just quickly, some other methods is that I did do a full seasonal analysis each season for 40 years. I used era 5 reanalysis. The composite blocking frequency is just the average or the number of events per season divided by the days per season. And when I refer to the NAO, I did use the index obtained from NOAA CPC. I did not use EOFs, which is a potential caveat of this work. But at the same time, EOFs, particularly in the North Atlantic, can be somewhat complicated. And so I did just want to keep it as simple as possible at first to really see the differences and similarities. Okay, so just to reiterate what we're really looking at here. And so altogether, we're looking at blocking analysis, particularly blocking analysis sensitivity. And so I mentioned we're doing each season. We're also doing classification of anticyclonic and cyclonic. We're also doing 2 different indices. And later on, I'll talk about how I broke it down into regions as well. So there's a lot of information. We're also going to talk about how this translates into the sensitivity of impacts to localized weather, as well as the sensitivity of blocking statistics. Okay, so now we're finally at the results of our first section, where First, we'll talk about the blocking frequency and then our blocking composites. Okay, so here is the blocking frequency by the PV theta index, right? So this is that PV theta index. And what we're looking at here is from the Northern Hemisphere, and we have the North Pole, and here's Florida, right? So we're looking top down, and we are looking at the total blocking frequency by season in each column and by classification in each row. Also featured is this dotted line, which is the seasonal climatological maximum 300 millibar eddy kinetic energy at each latitude. But essentially that just represents the jet stream here. Also featured is N, which is the total number of blocking events in each panel, right? And what really emerges is that we can see in our total panels 3 common blocking frequency maxima over Greenland, Europe, as well as the North Pacific. And these can be featured throughout each total panel, as well as in some of the classifications. But when we consider the breakdown into cyclonic and anticyclonic classification, the total percentage or N of the total blocking frequency is about relatively the same for each panel, right? So cyclonic and anticyclonic, there's no dominant classification of total blocking frequency per season. You really need to look regionally to see these differences. The biggest one that you can see here is the difference between cyclonic and anticyclonic blocking over the European region. Here you can see the cyclonic blocking frequency is much lower compared to the anticyclonic region. Further, most of the seasonality really just follows the seasonality of the jet stream. What we have, especially in the North Atlantic, is where I'm really focusing. We have this propagation of the cyclonic blocking frequency maxima from over Greenland in the winter to over the Northern Europe or Ural or Scandinavian region in the summer, right? And so most of the seasonality does kind of follow the seasonality of the jet stream. Further, this point does highlight that the results of the PV theta index are highly dependent on jet stream and jet stream variability, something to think about as we move forward. Okay, now let's move into our blocking composites. So when I refer to a blocking composite, what we're really looking at is the average of whatever variable, which the variables are listed here, for all block days across the 40 years. So we take all of our block days from our blocking events and take the average of the, say, SST anomaly during those blocking events. And so that is what a composite is. Further, we're considering our index, classification, and I've also included the NAO panels for comparison. Further, due to some of the differences in frequency maxima that we saw and how they can change regionally, it was kind of a motivation to break down these composites into Atlantic subregions, right? And so this better also highlights the impacts of each region than having an aggregate, right? Because if you have 3 different regions and you take the average of all of them, you're going to get a weak signal in the middle. This really goes into highlighting the impacts of what blocking in each region is or are, okay? Okay, so here are all of my plots, and we are going to go through each one individually. April Fools, I would never do that. But okay, so what I did do here is, as you can see, I've done 2 different plots. One of them is SST and precipitation, and the other is sea level pressure and 2-meter temperature anomaly. And again, I've done them each by season, classification, index, and also NAO. Luckily, I did break them down into simplified examples for us to look at, highlighting the main points. So here we have featured is the cyclonic sea level pressure composite over the Greenland region, also featuring our 2-meter temperature anomaly. What I've seen here is that there is some spatial consistency with 2-meter temperature signals in the composites, regardless of all of our classifications. so index, region, season, etc. But this is a nuance. There is a nuance to this result that it does depend on the placement of the anticyclone, right? So it is somewhat regionally dependent on where your blocking anticyclone is. The reason also that this is true is that locally blocking dynamics do alter the local radiation budget and also cause warm and cold air advection due to the cyclone. But again, this depends on where the anticyclone is placed, right? And so the intensity is really dependent upon the region. And this can be affected by multiple different things, such as albedo, soil moisture, local topography, etc. And does differ on an event by event basis. But moving forward onto some of our other classifications, we have our Greenland cyclonic, and then we also have our Greenland anticyclonic. And then we further have the results of the AGP or Z500 millibar index. A quick look that you can see is that the AGP results are much more intense compared to all of the other panels and does most resemble our NAO panel here on the left. And so compared to our noisier PV theta results, it does make me wonder if AGP is indeed better for extreme event analysis. But again, we'll talk about that a little bit further. So here we're moving on to our sea surface temperature, precipitation, and Z500 millibar anomalies. Okay, so very similarly, we're looking at our cyclonic blocking over the Greenland region. That looks like a block. It looks pretty good, right? And you can see our sea surface temperature anomalies. But here we can really see the usefulness of breaking it down into region. And so we look at our cyclonic blocking frequency over the European region and also our Ural blocking composite. And just looking at the differences between these, you can see some quite different signals depending on where you are considering the blocking region. However, our precipitation SST signals can only be attributed to the block locally. The rest is really to the larger scale pattern, right? So you can't attribute this precipitation anomaly to a block all the way up here, right? So really the point of showing these composites is to show the usefulness or how different blocking in different regions can be. Further is the difference between cyclonic and anticyclonic. And we can really see here is that we have this more like a standalone type feature versus a block that is kind of part of more of a larger scale planetary type pattern, right? So you have two different things going on here. And again, if we didn't classify into cyclonic and anticyclonic, you really wouldn't be seeing these differences. It would just be an average of both. So further, again, we have a really intense AGP or Z500 millibar index composite that really, really, really looks like this NAO composite. And while the Greenland one kind of looks like it has, you know, somewhat of an NAO-like structure, it doesn't really have this dipole that's really resemblant of the NAO panel. So across all of the panels, the AGP Greenland panel and the negative NAO are near identical. And that's something to just keep in mind as we move forward. Just to highlight that again, for each season, we have this difference between what cyclonic blocking over Greenland looks like compared to the full AGP case and the negative NAO. Doesn't really look like much in March, April, May. Finally, we start to see it in the summer and again in the fall, right? So only in about 2 out of the 4 seasons do we really see that cyclonic blocking signature really looking like the negative NAO. Further to highlight out of all of the composites is some ocean patterns of note, right? And so we do see this Atlantic tripole popping out. We also see something that I'm calling the higher tripole, where it's slightly shifted north here, and you have the signature, mostly due to European and Ural blocking. again, because of the local effects of the block. And then this like weird other ocean signature going on, and further, definitely some Gulf Stream variability. But I just showed this here as a highlight of some of the different patterns that really stood out, but I'm going to get into that in my future work. So conclusions of part 1, we have a classification of blocking into cyclonic and anticyclonic and by region, and it's proven to be useful, right? Because we have different signals throughout all of the composites. And we also saw some differences in the blocking frequency by region. However, the cyclonic and anticyclonic are about the same % of total blocking. It's really regionally dependent, and most of it follows the seasonality of the jet stream. When we considered the composites, we saw that weather variable signals can only be directly attributable to the block locally. The rest is to the larger scale pattern, but really does highlight the usefulness of sub-regional analysis, especially if you're trying to highlight the impacts of different places in Europe or in Greenland, that sort of thing. So again, it better represents the larger synoptic pattern and the impacts. And we also saw some open ocean questions. Further, we started to see this idea of an index sensitivity between the AGP and PV theta indices. The AGP index is dependent upon a threshold, whereas the PV theta index is more dependent on the jet stream. The AGP index was more intense across all composites, whereas the PV theta index captures the bigger picture. And the breakdown into cyclonic and anticyclonic did provide some insight onto potential different onset drivers. The AGP and Greenland panel and the negative NAO are near identical across seasons, where it was more of a weak signal compared for a cyclonic Greenland composites. So what we've seen here again is that we've highlighted all of these different little boxes, and we saw how they translate to the sensitivity impacts to localized weather. What about the sensitivity to blocking statistics? Further, we started seeing some differences associated with the NAO. And so what about the sensitivity of blocking with that, and how all of these things really play into or translate into different analysis? Well, we're going to be moving forward with that, highlighting differences in blocking statistics, particularly through the lens of blocking with the North Atlantic Oscillation. Okay, I just need a sip. Okay. So part 2, blocking in the North Atlantic Oscillation. Again, we're going to have a little bit of background, kind of talk about some different things, such as are they different, the correlation analysis, and some further index insights. So this is our background on blocking in the NAO. And no, this wasn't like a failed attempt at a Venn diagram. I really designed it this way to highlight these different camps in the literature of how blocking in the NAO are related, right? So you have this idea where the NAO preconditions blocking. You also have this camp where blocking and the NAO are the same thing. And then lastly, we also have this idea that blocking and the NAO modulate themselves, right? So one doesn't necessarily come before the other all the time. It's just that they have the potential to modulate each other, right? So we have these 3 different camps where some of them overlap and some of them don't. So really, blocking and the NAO are the same, not the same, and sometimes the same. And why does this even matter, other than it really just being my quarter life crisis? Well, if they are the same, if we can predict one, we can predict the other, right? And so this is the idea where we can improve the predictability of blocking through NAO predictability. And this idea was applied at both decadal and subseasonal timescales successfully. But unfortunately, blocking the NAO and trying to figure out if they're the same or not is really just a complex problem. And really, after doing quite a bit of analysis, I really like this idea proposed in Yao and Luo 2018, that blocking in the NAO relationship is an asymmetric spatiotemporal connection, right? And so it's essentially to me, when they're really just the lobes of the two overlap with each other. But again, deciphering the differences between the two, if any, with concrete conclusion requires much more advanced analysis. And yeah, so what can be gained from the blocking NAO relationship? So first, let's consider, when are they the same? Well, the short answer is, seasonally and instantaneously, because it was shown in Woolings and Masato, both who have used the PV theta index, there's really high correlation both seasonally and instantaneously. And so these are pretty high correlation values, enough so that it created this idea of the NAO and blocking being the same thing, and really only having a blocked and unblocked state in the North Atlantic. Further, in previous research of mine, using that AGP index, I've been able to get these really high correlation values. However, and as we'll see shortly, I was unable to really find that with the PV theta index. And where are they the same, right? And so there's a lot of notion of this idea of the negative west, positive east blocking NAO correlation shown in many early of the 2000s papers, right? So we have the negative NAO and blocking correlating strongly to the west, and positive NAO and blocking correlating strongly to the east in the North Atlantic, obviously. Even in Wooling's paper, the guy who said that the NAO is only blocked and unblocked, he did see some of that positive NAO over the Northern Europe. So this challenges, again, this notion that the NAO and blocking might not be the same thing all the time. So a common way to do this correlation, and again, I'm following the methods of these previous papers, is to do this regional averaging. And you take the correlation of normalized seasonal NAO and the normalized area average blocking count. And so I did that with that cyclonic blocking, as mentioned, or that high latitude blocking, where they were getting these high correlation values. And so here we have the normalized blocking count in this region with the NAO, and I didn't really get a strong correlation at all. And I tried many different areas, and the one actually featured here is the one used in this decadal predictability paper. However, cyclonic blocking over Greenland does not equate to NAO for this area, even though this paper for this area found a really high correlation, like negative 0.95 correlation. And so what we have here is a suggested sensitivity of correlation to region. However, there's another catch, is that this paper, compared to Wooling's, who used the PV theta index, used the AGP index. And I was like, hey, I have that, I can do that, I can compare. So I added that, and I was like, wow, this is interesting. And so when you compare against the AGP results, you get wildly different answers. And so what we have here is the sensitivity of this blocking correlation to index. And when you use the AGP correlation, you're going to get higher results, right? This is a stark difference between the two. And essentially what we can actually deduce between this time series analysis is that each index is actually measuring different blocking events, right? There's some key pieces being missed throughout here, especially when we consider this PV theta cyclonic index. And I did include total blocking, and I did even just for PV theta, and I did also consider the anticyclonic case. However, that didn't help the case at all. So again, AGP results getting really high, but even in the PV theta for Woolings, he got a high correlation as well. But we'll talk about that shortly too. So again, we have our indices are measuring different blocking events. Why could that be? So does it have to do with the vertical structure or height of the two PVU surveys versus the 500 millibar level? That was my first thought. The answer is no, after a couple of cross sections. Really is the attention brought to this paper down here, who did an index comparison study. And basically you have these different indices picking up on different portions of the flow field. And so PV theta could be misclassifying some blocks as jet streaks, or kind of picking up northwest of this anticyclonic center. Or is it a threshold problem based on the AGP? Because if you recall, it does take a certain threshold for blocking to be considered for that AGP index. Okay, so that's a potential explanation, is that it could be misclassification or a threshold problem. So again, just to recap, AGP index will result in a higher correlation. The indices are measuring different blocking events. And we have a suggested sensitivity of the correlation to region, right? Because I told you I did a couple of different regions and I couldn't find the correlation. So I was determined to find the correlation, and I did. But what we have here is, again, another multi-panel plot, but unfortunately we are stepping through this one, but I'm going to guide you through pretty well. We have our columns, our seasons, we have our PV theta cyclonic, PV theta anticyclonic, and our AGP index in the last row. Okay, first let's talk about the DJF case, because I finally found my high correlation with DJF cyclonic blocking in the negative NAF. And it is right here where my mouse is, very small, the size of one of these dots. And so it's a very small region where this correlation is happening. It's also much farther east than those in previous studies who won't even consider east of 30 west, okay? But there is still a pretty decent correlation here in the range of negative 0.55 and upwards, okay? Anticyclonic, again, doesn't really have a case, as previously mentioned, and does again highlight the usefulness of breaking down into classification. However, again, the AGP results lead to this much higher correlation. It's also in a different region and in a larger spatial extent. Okay, so again, these differences are highlighted, but cyclonic blocking over Greenland does result in a semi-high correlation in a very small area. Moving on, the seasonality of the blocking correlation does emerge into that negative west, positive east correlation pattern. And as you can see in these circles, even highlighted in the AGP index. It is shown though that the cyclonic is more significant to the west and anticyclonic more significant to the east. So I did mention that there is an eastward shift right here compared to Wooling's, who did it here. And that could be the difference, is why my correlations are slightly different than his. There has been a noted eastward shift in the wintertime NAO centers of variability between two periods. These two periods are encapsulated by Wooling's study, with the earlier study being farther to the west. I only have the later study encompassed into my study period, with another 20 years shifted later. This was shown that between these two periods, the difference is in the strength of background westerly flow. It was, however, concluded that basing conclusions based on these long-term NAO should be taken with care, particularly at short or 20-year timescales. So this really needs some further research and is actually, a pretty curious problem to be occurring. What we can conclude is that we do have a sensitivity to study period chosen, and that 20 years does matter when you're talking about the NAO, especially these longer term correlations averaged over 40-year periods. So the thing is, though, that the PV theta cyclonic index is capturing this potential change, whereas the AGP is not. Okay, so this could be due to the difference in onset criteria between the indices. Again, AGP needs a threshold where the PV theta does not. So here we have achieved a lot of things that we've looked at, all of our different classifications and index region, and how it translates to the sensitivity of blocking with the NAO. What about the sensitivity of blocking statistics? Well, I looked at duration, and again, I have my regions. Each box within here is a season, and then we have our cyclonic, anticyclonic, and AGP. Further, it's broken down into NAO tercile, because again, what can we gain that is useful between the blocking and NAO relationship? Well, overall, there's actually a pretty consistent signal throughout the durations of all the different classifications. There's no large differences, except with the AGP or the green boxes, which again are just jumping off the page. So what we can conclude from this duration analysis is that AGP blocks do have a larger duration than PV theta blocks. Okay, so we've checked all of our boxes. And again, let's highlight the conclusions of this second part. So using the AGP index results in higher correlation values than when using PV theta index over the Greenland area. We also saw that indices are measuring different blocking events. Further, we saw the sensitivity of the correlation to subregion with the negative west, positive east correlation pattern emerging. Lastly, we've seen that one index strength is essentially another index weakness. The strength of the PV theta index to capture variability associated with Rossby wave breaking in the jet stream compared to the strength of the AGP index for use in correlation analysis. So based on this, again, we have our dependent on threshold and jet stream, more intense. We have the breakdown into cyclonic and anticyclonic. These are all things we've seen before, except here we did find that it is indeed that the AGP index does correlate higher with the NAO than the PV theta index, where even though we did finally find a strong anti-correlation, it was in a very small region. We've also been able to conclude that each index is measuring different events. And one further concluding that the AGP index is better for established, more anomalous blocks, where the PV theta index might be better for capturing the onset due to the lack of threshold and ability to capture some of that variability. PV theta is also shorter in duration compared to the AGP, which is longer. So overall, from all of this and for me talking for however long, what have we actually gained? Well, we have a full climatology of classified blocks by wave breaking type that is regionally dependent and follows the seasonality of the jet stream. Why is this useful? Well, it's actually linked to sources of model frequency bias, right? So I mentioned at the beginning that we're pretty bad at capturing blocking frequency. So this could be useful in identifying some sources of capturing other phenomena, such as teleconnections and influencers of planetary waves. Further, we saw the correlation of the NAO and blocking, which does emerge into this negative west, positive east correlation structure, with positive NAO and anticyclonic blocking is higher over Europe and negative NAO and cyclonic higher over Greenland. But we did see the sensitivity of the correlation to all of these things, especially index. So why is this useful? Because like I kind of showed before, the NAO blocking relationship is well known, sort of, right? And what this is really showing is that it's a cautionary result that depending on the index you use, you could get wildly different results. And again, this does translate to blocking with other phenomena and impacts on weather, such as what we had seen in the composites. So again, using different blocking indices will result in largely different results when applied beyond blocking frequency. So AGP could be better for correlation and extreme event analysis based on the correlation and composites that we've seen, and PV theta better for onset studies and to understand smaller changes in variability. And lastly, part 3, blocking in the ocean. And so I haven't actually gotten fully here yet. And so what I do, this is more of my future work where I'm looking at different model runs and comparing how they may change blocking frequency and blocking statistics, right? So you might have to stay tuned for that one, but I'm really interested to see if classifying into cyclonic and anticyclonic can provide a lot of insight on some of these blocking frequency biases that we may have. So that's all I have. Thank you. Are there any questions? Should I stop sharing?
It's up to you if you want to leave it up, but if anybody does have questions for Kayla, I just ask that you can, if you want to, show yourself on your camera and unmute yourself and ask any questions.
Okay.
Well, I could start, sounds like. Kayla, interesting, lovely talk as always. I love the little rabbit going down the whole rabbit hole about indices. Yeah, it's always in studies of indices are there's a lot of non-uniqueness or arbitrariness or something. Sometimes the way to break that can be to either focus on the impacts. So, speak of regressions rather than correlations. They're related, but, regression gets you all the way to the units of the impact variable. And another maybe is predictability, that some of these are more the lead lag, and that can be done statistically just with like lead and lag. Are some indices more predictable than others? Even though they're correlated with each other, sure, they're partly redundant or something, but if one of them is more predictable, that might be a reason to favor it. Have you poked around with some of that?
I have not, but that is a really good idea and can really take, say, the PV theta index to that next level aside from the AGP index. So that's a really good idea.
All right.
Do I field the question? Okay. I can see that Paquita has her hand up.
Hi, yeah, I really enjoyed your talk. I thought your presentation style was great. I had a question about, you mentioned at the very beginning that weather and climate models have difficulty capturing the blocking events. And I guess to me that seems a little surprising given how large scale the features are. And so I was wondering what elements you thought were missing from or being poorly represented in these models that they have trouble.
Yeah, so I actually do think it's part of a larger scale planetary problem, such as like the Rossby wave breaking. So I think that's potentially part of the misrepresentation or missing, some things that might miss developing these Rossby wave breaks, if that makes sense, or creating that transition to create the Rossby wave that propagates across the North Atlantic and breaks, right? So I think it's a problem further upstream, if that makes sense. It really just motivated me to actually do that PV theta anticyclonic cyclonic breakdown. So.
Thanks.
Ben has a question.
Yeah, so first I wanted to comment on Paquita's question. It's a really good question, and I think some of these eddy feedbacks and for these PV folds, certainly the models really struggle with that, and I think that is in part resolution related. Even though we think 50 kilometers is enough for getting blocking right, but I don't think so for these eddy feedbacks and these folds. I think we even need 10 kilometers or something like that to get those things right. That's one thing. Kayla, I was wondering the question, if you went, pun intended, at the 30,000 foot level, what would be the one or two sentences that you would say that how is blocking different from the NAO? What's the, how would you explain that to someone who didn't go through your whole talk and didn't see? What would you say to Uncle Bob about what's the difference between the NAO and blocking? What is it?
I do think that it's a space-time problem, right? I think it's mostly a temporal problem. I've been starting to think of the NAO as more of blocks that never happened, right? Okay. So they kind of failed to develop. Where really, if you start averaging, especially at these longer decadal timescales, I think that this NAO signal that you're getting is actually a blocking signal, right? Because if you average it over a long enough time, you're really going to see a similar thing, and that's why that paper got a correlation of almost negative 0.95. Compared to a seasonal average of negative 0.8 and an instantaneous of negative 0.55, right? So I do think it's more of a temporal issue. And again, it's the NAO kind of represents blocks that didn't really have the chance to form.
Good, thank you.
Mary Beth?
I think my camera's going to be weird. Nice job, Kayla. You got me with your April Fool's joke. That was good. So you showed that there was a shift. I think it was like 57 to 77, and then the later years in like the region that you were looking at. And so do you think that that's a climate change signal in a shift of where the NAO and blocking is happening? Or is that some sort of like internal decadal low frequency variability?
That's a really good question, Mary Beth. And there is a paper that does suggest the greenhouse gas forcing playing a role, but it is an older paper. And so I didn't include it for that reason, but I don't think that there's enough information to conclude either way. I do think it's an open research question. I do think it's fascinating, especially how it could relate to how different blocking in the NAO could be in that region. Okay. I don't think I see any more questions.
Okay, great talk, Kayla. If no one has any other questions, I think we can end this session.
Okay. Thank you everyone for coming.
Thank you, everybody. We hope you have a great day. Kayla, thanks for joining us so early.
Thanks everyone.